This video looks at the pH of weak acids and weak bases. By the end of this video, you should understand why calculating the pH of a weak acid or weak base is different than calculating the pH of a strong acid or strong base. You should be able to calculate the pH of an acid or base from the Ka or the Kb. You should understand the 5% rule and why it allows for us to make approximations in our calculations. And you should be able to calculate percent ionization. Previously, when looking at strong acids and bases, we were assuming complete dissociation, meaning that the H+ concentration of the strong acid is equal to the initial acid concentration. However, due to the fact that weak acids and weak bases only partially ionize in water, the H+ concentration of a weak acid solution will not be equal to the initial acid concentration. Likewise for bases with the OH- concentration. Therefore, we must use Ka or Kb to determine the H+ concentration and then the pH. Consider this example. Here we're asked to calculate the pH of a 1 molar solution of hydrogen fluoride. We know that this is a weak acid, therefore the H+ concentration is not equal to 1 molar. First, let's consider the major species in solution. We have undissociated HF, H+, and F-, and we also have some H+ and some OH- from the autoionization of water. Notice the incredibly large difference between the K values. Since the K values are so different and the Kw is so much smaller than the Ka, H2O is a negligible source of H+, so we can focus on the H+ that comes from HF only. This will likely always be true for calculations we do with weak acids. I just wanted to be sure to point out that there is some contribution of H+ from the water. However, it is usually negligible. So, let's consider how to solve this problem. I'm going to start by making an ICE table. I stands for initial. We know that we initially had 1 molar HF, and since no dissociation has happened yet, we have no H+ and no F-. We don't know how much HF has gone down by or H+ and F- have gone up by, so let's call this value X. Due to the 1-to-1 stoichiometric ratio here, we know that if HF decreases by X, both H+ and F- will increase by X. Therefore, at equilibrium, we can subtract our change value from our initial value. From here, we can plug these values into our Ka expression. Our Ka expression then becomes 7.2 times 10 to the negative fourth, which is our Ka value, is equal to x times x over 1 minus x. This is H+ times F- over HF. This expression here could be somewhat problematic mathematically. However, since Ka is so small in this case, we expect x to be a very small value. Therefore, we can make an approximation. We can assume that x is going to be so much smaller than 1, the initial concentration, that we can actually drop the minus x from the denominator. This will greatly simplify our math. Now, with our new expression, we can solve for x and find that we get an H+ concentration of 2.7 times 10 to the negative second. If you don't believe that this approximation was okay, try it both ways on your calculator. Once you round to the proper number of sig figs, you should find that you get the same answer whether you drop the x or not, due to its small size. We're not done yet though. Now that we have an H+ concentration, we need to use it to calculate pH. So we take the negative log of the H+ concentration we just found and find that we have a pH of 1.57. Relatively low for a weak acid, but it was a relatively high concentration, so that makes sense. You may be asking if these approximations are okay. Generally, we follow something called the 5% rule. If the acid dissociates less than 5%, the approximations are valid. We can test this to verify. If X comes out to be less than 5% of the original HA concentration, the approximations are okay. So, thinking about this in terms of the problem we just did, we find that 2.7 times 10 to the negative second is only 2.7% of our initial acid concentration of 1. Therefore, this passes the 5% test. Generally, you can assume that problems we do in this class will pass the 5% test. However, if you ever get a large value of x as compared to your initial concentration, it's a smart idea to check on this. We can also calculate in the other direction. Consider this question here. Here we're given the pH of the solution and the initial concentration, and we're asked to calculate the Ka. As always, we start by writing the dissociation equation. Here I've chosen to do it without water, but you can do it with water as well. And then I write my Ka expression. I know that my pH is 2.9, so I can use this to determine my H+ concentration. Now I can use an ICE table. Initially, I have an acid concentration of 0.089 and no concentration of H+ or acetate. I now know that at equilibrium, our H+ concentration has increased to 1.3 times 10 to the negative third. Due to our 1-to-1 stoichiometry, this tells me that acetate has increased by the same amount and acetic acid has decreased by that same amount. Calculating equilibrium concentrations through subtraction, I get values that I can now plug into my Ka expression. After doing so, I find that my Ka is 1.9 times 10 to the negative fifth. Here's 2 problems to try on your own. Pause the video here, and when you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Now let's consider the case of weak bases. Recall that POH is the negative log of the H+ concentration, and that POH plus pH is always equal to 14. Just like we write Ka expressions for acids, it's possible to write a Kb expression for a base. Consider this hypothetical reaction below. Writing a Kb expression, we get an expression that looks like this. Here's 2 examples to try on your own. Pause the video here, and when you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice that the first case was a bit of a trick since NaOH is a strong base. Therefore, it's unnecessary to do calculations involving Kb. The weak base in the second example, however, does require the use of Kb. It's also important to understand how to get back and forth between Ka and Kb. Recall that the Kw for any aqueous solution at 25 degrees Celsius will always equal the same value. Therefore, we know that the Kw is equal to the Ka times the Kb for any aqueous solution. Given this relationship, if we have the Ka of a weak acid, we can calculate the corresponding Kb of its conjugate base, and vice versa. For example, consider the weak acid acetic acid and its conjugate base acetate. We can use the Ka of the weak acid to determine the Kb of the conjugate base. Given the Ka value from our table below, we can divide the Kw by the Ka of the weak acid to determine the Kb of the conjugate base. We find that the Kb of the conjugate base, acetate, is 5.6 times 10 to the negative 10th. Another handy concept that you might encounter is percent ionization. We saw this briefly when we looked at the 5% rule. Percent ionization describes the amount of acid that has ionized or dissociated at equilibrium. As you know, the stronger the acid, the greater the degree of dissociation or ionization, therefore the greater the percent ionization. This can be easily calculated by dividing the H+ concentration at equilibrium by the initial acid concentration, and then multiplying by 100 to turn it into a percentage. That brings us to the end of this video. Let's review our goals. First, we looked at how calculating the pH of a weak acid or base differs from calculating the pH of a strong acid or base. Then we learned to calculate the pH of an acid or base from the Ka or the Kb. Then we looked at the 5% rule to understand why it's okay to make approximations in our calculations. And finally, we learned to calculate percent ionization.